very welcome. This is Wireless Future. I'm Erik Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm great, and it's good to be back.
It's good to be back. It's been almost a year.
It has, and now it's 2025.
Now it's 2025. Wow, that's amazing. So today's episode 41.
It is.
It is. 41. Wow. What are we going to talk about today, Emil?
I was thinking we can talk about the new frequency bands that are being discussed for 6G.
New frequency bands for 6G. Wow. So this frequency bands, I guess I never really paid too much attention or had too much interest in all the specifics, but I certainly listened to a lot of talks and probably also read the occasional paper about different bands and how they are envisioned for 6G or even, 5G and 6G. And it seems to me that the general trend over the years has been to move upwards in the frequency domain, to use higher and higher frequencies, shorter and shorter wavelengths. And I suppose the main driver for that is that the higher up in the frequency domain that we go, the more bandwidth is available. But of course, the countervailing difficulty is that devices haven't been available for the really high frequencies. But now this discussion seems to be revived again with the 6G standardization. And there's this paper that you authored, Emil, enabling 6G performance in the upper mid-band by transitioning from massive to gigantic MIMO. Wow. Okay. So where do we start this? There are all these bands, FR1, FR2, FR3. Could you give us a background on what these bands are intended for?
Right. Yes, I think when it comes to the frequency bands, of course, we can measure all of those things in different gigahertz numbers, but people like to categorize them, and there are sort of two different main characterizations when it comes to cellular. One is what you said, FR1 and FR2. FR stands for frequency range 1 and frequency range 2. And these were the two different bands that was considered in 5G. And FR1 was then, from 0 or say 400 megahertz up to some 6-7 gigahertz. And then FR2 was the millimeter wave bands starting from, say, 24 and going up to, say, 71 or 52 gigahertz, depending on what people are saying.
So those are, let's say, the traditional bands that are being used in 5G. Then FR1 from, you said, 400 megahertz up to 7 gigahertz, and FR2 from 24 gigahertz to 71, that's the millimeter wave band. And now for 6G, there is a third one, FR3, that's on the table.
Exactly. So if people notice that there were a hole in between these two ranges, 7 to 24, this is what has been discussed as the potential place to place the 6G systems. And then it might then be called FR3, because it's the third band then to consider. And
right, so FR3 is basically there's a gigantic hole from like 6-7 gigahertz up to 24 gigahertz. There seems to be a lot of spectrum there. Why now? Were this big chunk of frequency never considered for 5G?
I think the main reason was probably that other systems were already using this spectrum to various extents. And then one saw that on the one hand, there were the possibility of deploying 5G in, say, the C-band, 3.5 gigahertz band. And then people were looking up towards the millimeter wave band as something that was completely unused, or more or less, at least, so that one could go there and not having to care about other systems at all.
Right. So what kind of other systems have been occupying this big chunk from 7 up to 24 gigahertz, up till now?
Right. So essentially all kinds of systems. So one can say there are links between satellites and the ground. And this might particularly be like fixed links for meteorological satellites or military satellites and things like that, or just backhaul for satellites. Then it could be different fixed links, wireless transmitters and receivers pointing towards each other using those bands, and there are radar systems and everything you can imagine.
Right, so you're saying that in this band from 7 to 24 gigahertz, I mean, in the past, pretty much every frequency there has been already grabbed by satellites and by fixed links and like weather, you said, satellites and other applications. So then why now suddenly can we grab all the spectrum for mobile communications?
Right. So the starting point here, I think, is that, we are looking for new frequency bands that could be used all over the world. And this is a spectrum range where we haven't harmonized very well how it is being used around the world. And then last year like a year ago, but it was in 2023 in December, there was the World Radio Communication Conference, which people are meeting every 4 years and discussing how to harmonize the use of spectrum in order to identify sufficiently large chunks of spectrum that can be used for new things. And that is when some specific bands between 7 and 24 were identified as, this might be a place for future cellular communication to operate, but we need to now spend 4 years to look into the coexistence with existing systems.
Oh, I can imagine. It must be a major difficulty to coexist. I mean, the spectrum, and also so many countries to harmonize the spectrum use among. So how does this harmonization among different countries really work? I mean, how do you get along around what band to use for what purpose?
Right. So in the ITU, the International Telecommunication Union, which is behind these conferences, they divide the world into 3 regions. And the first step is to try to harmonize within that region. So for us being in Europe, well, it's Europe and the Middle East and Africa. And then North America and South America is one region. And then East Asia and Oceania is another region. And you start to try to harmonize there and figure out, are there some specific frequencies here where we could potentially use the spectrum for the same purpose? And doesn't mean it needs to be all the spectrum between 7 and 24, but it might be, can you find some 200 megahertz or some substantial amount of spectrum that could be used without interfering too much? And then either move other applications out of there or design in future systems so you are mindful of the interference you might be causing to those systems.
Right. So, I mean, I can imagine this must be immensely difficult because presumably there are lots of like vested interests here in systems that operate in particular spectrum bands and can't easily be reconfigured just because somebody wants to grab that piece for mobile terrestrial comms instead. But you're saying that the way this process works is to start like in regions and then get along within the region and then hopefully over time harmonize among the different regions as well.
Right, and there are some examples of how these things are being done. So some of the same frequencies are being used for fixed links on the ground. So you're pointing a transmitter and receiver towards each other. You have a substantial directivity towards them. And then at the same time, you use the same spectrum pointing from the ground up into the sky to a satellite. And that can be done at the same time.
Oh, they can be done at the same time. I mean, that sounds like a nightmare for the satellites if they are subjected to interference from a terrestrial link. Because, I mean, even though the satellite's far away, but it will be in line of sight. So you'd have to be very careful, I suppose, with the antenna diagram or even with null forming to make sure not to create interference. Or how does that really work?
Yeah, exactly. So it's easiest to do it for fixed links where you can actually deploy your antennas to make sure that the radiation up towards the sky is very small. And
it's very small.
Yeah, and then if you know where you are on the ground, if you also have like geostationary satellites, you know where they are going to be located, well, then you can actually make sure that you deploy it in such a way that the interference is sufficiently small.
Huh. So is this done with like fixed gain antennas or with adaptive phased arrays, or how is it how do we ensure that we don't spread interference to satellites?
Right. So I think for the fixed links between two fixed locations, you can do it with like fixed gain antennas that you deploy in the right way. But of course, the challenge that you are alluding to is if we would now start to use the same frequency bands for cellular communications, where maybe we can control how the base stations are transmitting down towards the ground and limit the radiation upwards, well, we still need to make sure that how do we handle the user devices, which typically spread their signals all over the place. Of course, they are weaker, but it's a challenge.
Yeah, I mean, it would be a major challenge for a mobile user, I suppose, because even though you theoretically could form a null into the sky, into the direction where a satellite is located, number one, you would need a lot of aperture to pull that off, and number two, you would need channel state information to actually know where that satellite is located. So that seems like a challenge, right?
Yeah. An easier solution would be to not use the resources at the same time or frequency. So either that you know that you only occasionally transmit up and down through the sky, and then you make sure that at that times you're not transmitting anything on the ground, or you use a frequency band which is adjacent but not exactly the same as on in these two different systems, and then you still have the out of band emissions that you need to deal with, but that is somewhat easier to deal with.
Yeah, at least, I mean, those are like 40-50 dB below the in-band emissions, but still I'm thinking like, so you're saying that suppressing interference would not happen through spatial beamforming, but rather by staying away in the frequency domain and maybe in the time domain?
Well, I don't know exactly what solutions will be utilized in the 6G cases, but I think these are the kind of things that are being looked into now, running simulations first perhaps, and then trying to make actual measurements, because there are some specific things that are really sensitive. It could be radar systems used for, it could be flights, aeronautics, or it could be for meteorological things or other kind of Earth operations that where just a small amount of interference will reduce the precision, and then you really need to test these type of things. And I think already now in 5G you have certain locations in Sweden, for example, where you have this kind of systems deployed, and then if you're nearby those systems, you are not allowed to use the same amount of power as if you're further away.
Right, I can imagine, because a lot of these systems operate on very tight link budget and perhaps need rather high signal-to-noise ratio as well, so that you become very sensitive to any interfering signal from out of system. But I would still imagine, I mean, it'd be a major challenge from a mobile terminal to avoid creating interference through spatial processing to start with. Maybe aperture won't matter so much, but you would need a lot of antennas to form a lot of nulls, and you would need very high precision channel state information to place those nulls, which seems like, I don't know whether that'd be feasible at all. So, seems like a challenge, yeah. Wow.
Right. But in any case, what is now being looked into from the last conference to the one that is in 27 are not the entire band between 7 and 24, but some specific ones. There were 3 that were identified. One is between 4.4 and 4.8 gigahertz, and that is not a huge amount of spectrum, it's only 400. Then there is a large one around 7.8 gigahertz, and depending on the region of the world, there might be like 1.5 gigahertz up to 2 gigahertz of spectrum there. And then it's around 15 gigahertz. So these are the 3 frequency bands that are now being looked into as potential places to allocate for cellular. And this essentially means that if we want to deploy 6G in a new band and not trying to take a 5G band and convert it into 6G, well, it's probably these 3 different bands that one should pay attention to, because 2027 is the last occasion to harmonize the spectrum usage in the world before we'll be deploying 6G networks in 2029 or 2030.
Oh, so this harmonization has to happen within the next couple of years, you're saying?
Yeah, the decision needs to be made on this next World Radio Communication Conference in 2027.
Oh, the next World Radio Communication Conference, wow. So you said there were like 3 bands that are considered. One is a 4.4, you said?
Yeah, 4.4 to 4.8, so let's call it 4.6.
Yeah, 4.6. Okay. But the 4.6 actually, does that still belong to FR3? Because you said earlier that FR from 400 megahertz up to 6 gigahertz is the FR1. But now it's like they intermingle a little bit. Seems.
Yeah, no, exactly. So it's not entirely that simple of saying that we are only considering the area between 7 and 24.
All right.
But I think that among these three bands, I would say that the 7.8 band, that is where you can find a substantial amount of new spectrum to make it really worth deploying new base stations. So I think that is the main thing there, and potentially this 4.6 band might be used as a carrier aggregation to a 5G system that is already operating if you're developing the technology.
Right, I see. So we are oversimplifying slightly here, then, but there are really three new bands that are being considered. One is at the 4.6, the other one is around 7, and the third one is around 15. And it's really up there at the 7 and 15 where we can find these really big chunks of virgin, unused, totally new for 6G spectrum that could be used more or less without any constraints from legacy technology or deployments then?
Well, I think that if you take this 7.8 band, there might be up to 2 gigahertz of spectrum there in total, but most likely you will only be able to identify some pieces of it that can be used. So I think that maybe you will find at most 1 gigahertz or even less than that. And what typically happens is that in the country you have, say, 3 physical networks, and you have more telecom operators than that, so they're usually sharing infrastructure. And if you in 5G now typically have like 3 physical network with 100 megahertz each, you might be doubling that to 200 megahertz and have 3 networks, and that would mean some 600 megahertz in total. So I think this is the ballpark numbers of amount of new spectrum one can expect to actually come out of this.
Right, so those are the ballpark numbers. I mean, but you said like in 5G, an operator might have like 100 megahertz, and now in 6G, that operator might get like 200 or maybe 300. So that means like a doubling or tripling.
Yeah.
But I thought 6G was going to get like 10 times as fast in terms of data rates and capacity, but it sounds like it's only going to become the double or maybe 3 times.
Right. So you're right that the goals of 6G are also something that this ITU organization is putting out, and they are specifying that maybe it is 10 times faster you want it to be, or even more than that. And it then seems clear that if we should reach those goals in these bands, well, you can't get all of it from having just more spectrum. We need to use something else. And what could that other thing be? Well, our favorite topics of MIMO communications, so having even more antennas.
Of course, MIMO and even more antennas.
Exactly.
So what does that mean concretely? I mean, so we got already MIMO, right? Or massive MIMO with something like what? 64, 128 perhaps antennas currently in the panels. I mean, in 5G deployments.
Exactly, and some 4 antennas in the user devices.
Yeah, 4 antennas in the user devices. So now speaking MIMO, I mean, I suppose the MIMO would be used for multiplexing here chiefly. Yeah? So to send multiple streams to multiple users at the same time. But how are the propagation conditions in these new bands? Because the higher we go in frequency, the more it seems to me that the more line of sight we will see and the less of scattering, which might be challenging for MIMO in general. Right.
So if one starts from thinking that the base station and the user device will have a certain size of where they can place the antennas. So the base station have a fixed panel size. The space in the mobile phone we can squeeze in antennas is also fixed. Well, in those situations, the antenna elements, if for a particular gain of an antenna, shrinks with the wavelength. So you would need less space per antenna. On the other hand, you need to fill out that same area in order to get similar received power. So if we say that we roughly double the frequency from today's networks in 3.5 up to 7.8, and then you deploy antennas in 2 dimensions, well, then you can have 4 times the number of antennas, both in the base station and in the mobile phone. And we need to then use those antennas, and that could potentially give us, to every user device, 4 times more spatial beams that you can transmit to the user in the right kind of propagation environment. But as you're saying, propagation conditions, the channel between the transmitter and receiver could still be more complicated.
Yeah, sure. Right. So the basic point here is that, I mean, the aperture has to stay the same to maintain the link budget. But then for a given aperture, when we go up in carrier frequency, we can squeeze more and more antennas.
Right.
But of course, that array that we build will also be more directive then. So it becomes critical to gain accurate channel state information and know how to actually steer these beams.
Exactly.
So how many antennas do you envision that a base station will have for these new bands?
Well, I think before we talk about that specifically, I think what you were saying is correct, that at the receiver side, if you are filling the same space with antennas and get some 4 times more antennas there, then when you do the same at the transmitter side, you get more directivity. And that more directivity is actually beneficial in a line of sight scenario where the transmitter and receiver sees each other. You can actually get 4 times stronger signal at the receiver. So often people are having this impression that if you go up in frequency, you get worse propagation conditions. But actually, if you are doing your antenna design properly, you would get a stronger signal in line of sight scenarios. So that's a good starting point. Still, when you go down and deploy your cellular networks, there will be various kinds of materials in between you and the receiver in many situations, like glass and wood and concrete and all this type of things. And one of the things that people are looking into now is how can we model those propagation conditions. Are they much worse than in the lower bands that we've already been using? And it seems like for glass and wood, it's roughly the same. Maybe you lose 1 dB more, but for concrete, you lose substantially more, 5, 6, 7, 8 extra decibels of losses. So that's a challenge.
But that's actually a good point. I mean, so you're saying that if we're looking at just a point-to-point wireless link and let's pretend that we have an omnidirectional transmit antenna, then we only need to scale. I mean, we want to maintain the receiver aperture constant with respect to frequency, which means when we go up in frequency, we pack in more and more antennas. So double the frequency, 4 times more antennas to maintain the same SNR. Now, if we were to build an array also at the transmitter side, then we could get an additional gain from that, in fact, because the transmitted beam will be correspondingly narrower and narrower. So either we would need a larger aperture at the receiver or at the transmitter, or both. But if we go with a larger aperture at both the transmitter and the receiver, then these apertures they could be correspondingly a little smaller, is what you're saying.
Right. And I think that if you really want to be successful with deploying these networks at, say, 7.8 gigahertz, then you want to maintain the physical sizes where you put the antennas to be the same at transmitter and receiver, getting this power gain in line of sight scenarios so you can handle a bit more losses in non-line of sight scenarios. And then there is some claims being made now by companies like Nokia that if you do this right, you can deploy your base stations on the same locations as you have 5G base stations today and get roughly the same ranges, and you can benefit from this extra amount of spectrum all the way to the cell edges in the current grid of base stations. So you will not have to densify much more.
So how many antennas do you envision that the base stations will have for these new frequency bands?
So if we say that antennas today, or base station panels today have, say, 64 antenna ports, then you might go up to 4 times that. So 256 in the 7.8 bands, and maybe go all the way up to, say, 1024 antenna ports if you go up to 15 gigahertz. So there are large numbers, and actually when you build something like this, you have more smaller gains antennas, because usually even if you talk about, say, 64 antenna, this is not the number of physical elements you will see if you open up the box, because each antenna port that we can control from digital baseband typically contains some 3 to 4 smaller elements that are fed with the same signal to create a stronger gain antenna as well. So there will even be hundreds to 1,000 or 2,000 of antenna elements inside these boxes.
Oh, so you're saying that the panel might have like 1,000 antennas in total, but they are interconnected, hardwired with like a Butler matrix or something, so that the actual number of antenna ports is much smaller.
Yes, exactly.
But it also means that they have like an intrinsic directivity through the way that they are wired.
Yes, exactly. And there are some reasons for that, because on the one hand, we want to get that gain that we talked about. We need to fill those apertures with small elements so that we can get that maximum gain in order to get decent propagation conditions. On the other hand, why do we like to control every element individually? Well, we can steer beams as we like in all possible directions.
Yeah.
And if you can do that, you can also send many beams and do spatial multiplexing, serve many users at the same time, or send many streams to the same user. And you probably want to do that, but maybe not do it immediately with 4 times more streams. So therefore you try to find these kind of trade-offs where you have more antenna elements, but not control each of them individually.
Right, so the key thing here is to actually fill the aperture with antennas at half a wavelength spacing. So on receiver, I mean, this is all easiest to understand on the receiver, so that you can soak up all the power that's impinging on the aperture.
Exactly.
Yeah, great. So now, isn't this just massive MIMO? I mean, you've been using this term gigantic MIMO for, I don't know, arrays with like 1,000 maybe or more elements, but to me it's all massive MIMO. It's just a matter of scale. Do we really need like a new term for for that?
I think this is a great point, and I think when you and me started working on massive MIMO, then it probably meant something like everything from 100 antennas up to infinity, and a lot of the papers in the early days of massive MIMO research was really looking at this limit where the number of antennas becomes so large that they are indistinguishable from infinity. Then when you actually starting to deploy real networks and use massive MIMO as a marketing term, well, then it has been associated now with 32 and 64 antenna ports in the base stations. And then I'm thinking that if we should now in 6G have something that is bigger, say 256 and upwards, then we need a new term. And then,
right. So when you say 256, you mean antenna ports or you mean antenna elements?
Mean antenna ports, yes.
Antenna ports, yeah. So the actual array might have more elements.
Yes.
It's just that they're hardwired through like small Butler matrices or something that makes them intrinsically directive spatially. Got that, yeah.
And then I made up this new term gigantic MIMO for a reason, because there are a lot of other terms that already existed that people have been suggesting in the last few years. People have been talking about extremely large aperture arrays, extra large MIMO, ultra massive MIMO, and often these terms have been associated with either terahertz communications, so entirely different frequency bands, or they have been connected to near field communication effects. And I wanted to say, well, we want a term that is not connected to these other kind of things. I was studying that context. We want a new term, and then I essentially asked ChatGPT, what is bigger than massive? And it suggested gigantic.
Gigantic. Okay, wow. All right. So now let's recap. Let's break this down. I mean, again, so you said massive MIMO is up till 64 or maybe 128 antenna ports, and then gigantic starts at like 256. Is there a limit how high you can go and it's still called it gigantic, or will there be in like 10 years, will there be another new
Yeah,
superlative
we probably need to find eventually a term that is bigger than gigantic, whatever that might be. But let's see what kind of products comes out there in the 6G era. Maybe it will go up to 1024 or even more than that, and then we will need to have something even bigger than gigantic in the end.
Yeah. To me, this all comes down to how efficiently we can build the actual microelectronics. I mean, in turn, that comes down at some point to cost, but fundamentally to power consumption and complexity of these systems. So one concern I have with going up in frequency is that the coherence time shrinks, which makes it more challenging to estimate channels, because the time it takes before a channel estimate is outdated shrinks. And one consequence of that is that it gets progressively more difficult to multiplex a lot of terminals simultaneously, because you want to give these terminals mutually orthogonal pilots, and these pilots have to fit and be orthogonal within a coherence time window or coherence block. And now we go up in frequency, that coherence block shrinks, which means that the number of orthogonal pilots that you can construct gets fewer, which means you can multiplex fewer and fewer users altogether. So there seems to be like a contradictory effect here that, well, going up in frequency, we want to build larger arrays, larger in the sense of number of antennas, which theoretically could allow for more massive spatial multiplexing, but at the same time the coherence time shrinks so that the number of terminals or mobiles that we can effectively learn the channel to will decrease. Is there a sweet spot, I mean, in terms of like frequency here, or
right,
or how does this play out?
Right. So I think that the telecom industry tries to view these new bands we're talking about as the golden band, the thing that is great in every aspect. It has sufficiently enough amount of extra spectrum. It has propagation conditions that are not too different, so we can use the same site grid. But then, as you're saying, coherence time will certainly be a challenge. So if we build a system exactly based on 5G and place it in these new 6G bands, if you have twice the carrier frequency, you only have half of the resources per coherence time. So we will need to be more clever when we are doing the channel estimation. And I think this is something that the standardization now, when it starts, need to really pay attention to. And we have been advocating a lot about letting the user device send these pilots and then estimate the channels in the uplink at the base stations. And in that way you can support arbitrarily many antennas in the base stations. But you, on the other hand, have the challenge you're saying, if you want to send pilots from multiple user devices or send multiple ones from the same device in order to be able to estimate multiple beam directions from the user's perspective as well. Well, you have this challenge, and I don't think we can cheat the physics. What we can do is to sort of narrow down what are the actual use cases. If we instead cut the maximum speed that we allow a user to travel at, then we can gain back the coherence time a factor 2, for example. And if we cut it by a factor 4, well, then we can also handle twice the number of users in these bands as well. So I think it is playing there. Maybe these bands are not meant for high mobility. Maybe we want to use lower frequency in those cases and then use this for more indoor users or slowly moving users in cities.
Right, that's a good point indeed. So a lot of users might not be so fast moving, and then we could use the lower bands for those who actually move fast, and the higher bands for those who are more stationary or perhaps indoors. But in terms of channel estimation, and I mean, what is the intended duplexing mode in these new bands? Would that be TDD uniformly across the board, or is FDD also being considered?
I think that both possibilities are out there. I think this it has some connection to also the coexistence with other systems. I still think that TDD is what people are mainly considering, because this is the way we have been moving. But then some of the satellite systems, for example, are operating in FTD modes and only have one of their links coexisting in this area as well. So there are these things to figure out, certainly.
Yeah, interesting. Wow. I mean, I'm a TDD reciprocity guy, as you know, and probably you are too, Emil. But
right.
So I believe that a technically sound design should rely on obtaining channel state information from uplink pilots. And then, of course, now if coherence is tight, you could augment that estimation by, for example, by utilizing prior information on the channels or parameterized models or second-order statistics or you name it. But fundamentally, the advantage with estimating the channel from uplink pilots and exploring reciprocity and operating in TDD is that the pilot overhead is independent of the number of antenna ports at the base station, which seems like an important thing now that we're moving to this gigantic MIMO panels with 256 or even more antenna ports.
Right. And I think some of the things you're describing are just clever algorithms that people will hopefully be able to implement and utilize this kind of prior information in some way. But I think in standardization, they will also have to modify how these uplink pilots, also known as SRS or sounding reference symbols, are implemented in 5G, because we've been advocating for that you send a sequence that every user have a pilot sequence that spans a number of channel uses, and that but what you actually have implemented in 5G is that users take turns on transmitting, and the difference between these two things is a little bit technical, but it certainly means that you get less power for your pilots when you take turns instead of sending long sequences that are orthogonal to each other, and therefore you get lower signal to noise ratio in the uplink pilots. And when you then have smaller antennas in 6G, you will have even lower link budget unless you're playing this game right in the standardization of uplink channel estimation.
Okay, so that's something I guess I never thought about really, but you're saying you get lower signal to noise. It sounds like something we probably should return to at some point, because I'm not totally sure I understood here what was going on. I mean, in a way, the signal to noise ratio should be just dependent on the integration time.
Right, but you don't integrate over time.
Say again?
You don't integrate over time.
Oh, you don't integrate over time.
So if you have 10 different sequences, what you see in textbooks is that you get a spreading gain or a processing gain of a factor 10, because everyone sends a 10 length sequence and then you take all the power out of that. But that is not what you do in real systems. You send one at a time and you don't get that kind of 10 times gain.
Oh, so you send one at a time, but you don't integrate coherently among them. Then, of course, you get no power gain or SNR gain. Interesting. Okay, yeah. I mean, it's a technicality, but it sounds like something we probably should return to at some point. It's an interesting little quirk. So now there is this goal, I think, set by the International Telecommunications Union, ITU, that 6G should achieve a peak rate of 200 gigabit per second, and that a typical rate offered to a user should be half a gigabit. Will we be reaching that?
Yes, these targets are always very interesting, because I think for 5G we're supposed to have some 20 gigabit per second peak rate, and now that they want it to be 10 times bigger in 6G.
Yeah.
I don't know if I have ever seen any device reaching 20 gigabit per second. I think you can do this if you combine millimeter wave with 3.5 bands, and you can create this kind of scenarios where you can reach it. And you can definitely do this in 6G as well. So say that we take this entire 7.8 gigahertz band, take all the spectrum there, then you do some, say 16 spatial layers of MIMO to one device. Today you can do 4, let's take 4 times more than that. And then you are taking the biggest modulation sizes that you have radio hardware for today. So I think in Wi-Fi 7 you can do a 4096 QAM. If you multiply all those things together, you can reach some 200 gigabit per second. So it's technically possible in these bands. It's just extremely unlikely that you will ever build something that can support that. But I think that is what you have in mind.
Yeah, I guess one question is, what applications would actually require 200 gigabit per second, right? And then you're right, theoretically, if you're close enough, so the signal to noise ratio is high enough, then and phase noise is low enough in your receiver, or you could compensate somehow or track that somehow and compensate for, you could use 4096 QAM or even higher modulation and you could get there. But that's not to say that it's realistically would be built or used at any scale. No, to me, some of these numbers just come across as marketing figures that now we got 5G and now we need a new generation systems and therefore everything has to be like 10 times as massive, 10 times as high peak rates and 10 times as many antennas and 10 times as more spectrum.
Right. So what this really means in practice is that ITU will have to provide a certification that a new technology can be called 6G. And then 3GPP, who is creating the standardization or creating the standard, they will have to eventually show their blueprint. This is what you can theoretically, with the similar calculation that I was doing, this is what you can deliver if you have all the spectrum that you theoretically could support in the standard. And they say, okay, fine, then it's 6G. But probably this average or more what you call a typical rate, it's what's really important.
Right. Well, I think what's important is like, what can we offer at the cell edge? What can we offer to the most disadvantaged users? Because in the end, my feeling is that a lot of customers, that's what they will be willing to pay for. What can we guarantee that they will always get? And then anything above that is a bonus. Yeah, it's great if you stand in line of sight, you get your 200 gigabits, but what really matters is that your system works. No matter where you are, you get at least some connectivity, at least a couple of hundred, say, megabits of throughput.
Right.
So
if you get these huge speeds, it's not like your computer game will go faster or your movie will run faster or anything like this. It will rather be that your device will only be scheduled part of the time so that you bring down the actual rate to what your user service needs. But you were saying that 0.5 gigabit per second is sort of what they call a typical rate in 6G that you like to support at the cell edge. This means that say 95% of the locations in your cell, you should be able to get at least 0.5 gigabit per second. And of course, one will have to go out and measure this. But we did some simulation in our papers and saw that thanks to the combination of having more spectrum and having more antennas, which were actually, according to our propagation simulations, giving you a higher MIMO rank as well in practice. The combination of these things led to that, yes, you can reach this 0.5 gigabit per second to, say, 97-98% of the locations in our 1 by 1 kilometer deployment area.
Mm-hmm. So 500 megabit per second to 97% of the users. That sounds like a pretty good sales argument to me. Wow. So now with these new gigantic MIMO arrays and in all this new spectrum, will we be operating in the near field?
Right. Yes, that's an interesting question. So we've been talking about this radiative near field where you see beams of different shapes focusing of signals in not only angle but in depth domain, for example. I think we talked about this already in episode 22. I've been spending a lot of time analyzing this myself. And then, if we say that we have a particular propagation distance, we should compare this with a number called the Fraunhofer distance, which is where the far field, where the classical propagation condition starts. And if you have half a meter wide array, which is what you probably have in your antenna panels in the future, and then you take 15 gigahertz as the largest frequency, and we have half a wavelength space in between there, then the Fraunhofer distance is say some 23 meters. And typically you are not closer than 20 meters to a base station, it's probably more than that. So
no.
Yeah.
So then the answer would be no. I mean, to be clear, and I think this is an important point to drive home, that reciprocity-based beamforming in massive MIMO makes fundamentally no assumptions on what the propagation channel looks like, which means that works equally well in far field or near field or anything in between. So what happens is that when you have a large aperture or an aperture that's large relative to the distance that your mobile user is away from it, then you get this near field effect, which means that with reciprocity-based standard, classical, old-fashioned by now TDD multi-user MIMO beamforming, you can multiplex to terminals that are located in the same angular direction but at different distances from the panel. But you seem to suggest here that this effect is not going to become very important. I mean, it might not be very important in 5G, and it doesn't sound like it will become very important in 6G and with gigantic arrays either. Is that so?
Possibly. So for this array deployment that I was mentioning, it will not be important. If it were important, then when we talked about channel estimation and using prior knowledge, if we knew that near field effects would be there, that would be some kind of prior knowledge to put into such algorithms. But there are reasons that you might want to get these near field effects, because then from one base station location you can focus signal power not only in angle but in also depth, and that can be useful in order to try to reduce interference between nearby users, or in order to use signals not only for communication but also to localize users both in angle and in distance. So those kind of effects are there, and then we start to think about how could we do something like this. And if you think about yourself, you have some kind of depth perception yourself, because you have two eyes that are separated by quite a large number of wavelengths using the visible light. So if you in the same way would take one antenna panel and you pull it apart, split it in half and move it some meters apart, say 5 meters away from each other, then all of a sudden you have two antenna panels, both of them seeing the receiver even more in the far field, but together they could phase align the signals and create some kind of near field like focusing effects.
That's right. So basically that is DMIMO, right? Distributed MIMO. So effectively you're enlarging the aperture, and that has a lot of benefits. I mean, one, as you suggested, is that you can separate users that are located in the same angular direction but at different ranges. Another benefit, I believe, is that you might be able to, or you can multiplex multiple streams to a multi-antenna user.
Exactly.
Right, which is where like one of the main benefits of DMIMO technology.
Right. And I think if DMIMO or distributed MIMO is just generally the concept of having antennas that are not close to each other in one array, but there are multiple maybe arrays at different locations, then the most attractive way of deploying that in practice, I think, is for a telecom operator to deploy it all on the same rooftop, because they're used to deploying, say, 3 different antennas panels on the same rooftop pointing in 3 different directions. And if they now within the same direction put 2 smaller panels instead of 1 bigger one, or 2 normal sized panels, well then that could be an attractive deployment. You would have all the cabling next to each other, you will have all the computing power somewhere nearby as well, so you can more easily phase align the signals from these panels as compared to just spreading out the antennas arbitrarily in the city.
Right. So that would be some sort of rooftop version or rooftop light version of distributed or DMIMO then, or cell-free MIMO, right? That makes a lot of sense to me. You mentioned phase aligns. I guess one of the technical challenges here is to actually synchronize these different panels in phase, which is going to be highly important for uplink. That's not such a big deal because pilots and signals and data signals see the same channel, but on downlink with reciprocity-based CSI, they will have to be phase aligned. And another thing that I suppose would happen here is that we will be getting grating lobes. I mean, once we depart from uniform linear arrays with half wavelength spacing, then the antenna pattern will exhibit grating lobes. But that shouldn't matter as long as we operate again in TDD with reciprocity-based beamforming. Then grating lobes don't matter. To me, that seems to be a bit of a misconception that's still around, that grating lobes could be a problem, but in fact they will not. As long as we measure channel state information from uplink pilots,
right,
they will not make a difference for the beamforming.
So this concept of grating lobes are normally analyzed in textbook for a case where you have uniform linear arrays, so the spacing between all the antennas are the same and they are like in one direction, and then when you have larger than half a wavelength spacing, there will be some angular directions that are getting a strong signal, equally strong as in the intended direction. But in what I suggest here would be that you don't have uniform spacing everywhere. You have two panels with small spacing between them. Each one of them are then transmitting a signal without any particular grating lobes. And then at the location where the two beams are crossing each other around the user, you get an amplification. And there can certainly be other places where side lobes will also add up together, for example, but you will not get the classical type of grating lobe from this deployment either, in the sense of that you have other locations different from where the user is, where you get a equally strong beamforming gain as on the location of interest.
Exactly. So what I meant is that if you have a uniform linear array with, let's say, lambda half spacing, and you form a beam in line of sight, then you'll see this beam with some side lobes. Now, if we stretch the array out, so we enlarge the aperture and increase the spacing between the antennas, and then we form a beam, we will start to see grating lobes. And the grating lobes will appear there. The main lobe will correspondingly get more narrower. But as long as we have perfect channel state information, those grating lobes make no difference whatsoever for the link budget, so for the received power at the intended destination, nor do they make any difference for the interference situation on average. But maybe that, I mean, this is getting very technical now, so it sounds like a topic that we maybe should say for the future at some point.
But just to wrap it a little bit back, there is a connection between grating lobes and coexistence with other systems as well, because then you don't want your grating lobe to aim at the satellite in the sky or anything like that. So
but that's a great point.
So that is why I think people were very obsessed with this grating lobe concept back in the days.
Yeah, but that's a great point. For coexistence reasons, you might not want grating lobes that point up in the sky. So it seems to me it opens a lot of new opportunities for design of, I mean, beamforming algorithms by all means, but also antenna topology designs that function well in these scenarios where you have coexisting applications to consider.
Right, but to pick up on the thing you said before, that this kind of multi-panel deployment would be a first step towards distributed or cell-free MIMO. I really think that this might be the journey there, because when you and me have been working on this cell-free MIMO case with the idea that instead of having really advanced base station with a lot of antennas, you would spread out the antennas over the city, and that would be more optimal from being always close to some of the antennas. And if you then control them jointly in a distributed MIMO fashion, you can also deal with interference. So this would be great, but it also very different from how telecom operators are used to deploy their networks. So I think that starting from the point where you on every base station locations deploy multiple panels, and then you gradually connect them together and maybe deploy some extra antennas here and there, that could be the natural journey towards some kind of cell-free like MIMO topology eventually. But this might not be what we will see in the beginning of the 6G era, but maybe later on.
Right, there's a way of organically moving towards the MIMO, starting off by connecting panels that sit on the same rooftop, and then perhaps eventually connecting, as you said, more and more antennas, and eventually connecting then everyone within the cell, so that it can operate phase coherently together. Wow, yeah, that's an amazing vision, in fact.
So I think one thing that we missed talking about in the beginning, we mentioned the terminology FR1, 2, and 3 for frequency bands. There is another parallel terminology, which has been the low band, the mid band, and the high band, where the low band was below 1 gigahertz, the mid band was from 1 to 7, and the high band was the millimeter wave band. And now this new chunk that we've been talking about today, 7 to 24, what you want to call that? Well, people are starting to call it the upper midband. So they connect it together with the midband where we are using 5G today, and they call it the upper midband.
Yeah, so the 7 through 24 gigahertz that constitutes the FR2, that would fall into the upper midband.
Yeah, the FR3.
Low, mid, high terminology. Yeah. Oh, sorry, the FR3. Yeah, correction. The FR3 band from 7 through 24 gigahertz is envisioned to be like the main source of new spectrum for 6G. That would fall into the upper mid-band in this low, mid, high terminology.
Yes, exactly.
Super. Yes. There we go.
Yes. So it seems quite likely that this is where 6G bands will actually be, and the future will tell exactly what frequencies and how things will be happening there. But I think that we will find some new spectrum there, but maybe the biggest gain, if you want to achieve some 10 times higher data rates, will not come from having 2 times more spectrum, but having maybe 4 times more MIMO, and these type of things together will lead the way towards 6G performance.
So more spectrum, more antennas, more MIMO.
Yes.
That's where we're heading with the 6G.
We are.
Yeah, great. So, well, thank you, Emil.
Thank you. A great way of kicking off 2025.
Indeed.
Thank you very much.